Good morning, statistics scholars. Today is Thursday, May 8th, and I cannot believe how much I miss being with you, how much I miss our conversations. So much has happened since to me since I saw you last. I'm looking forward to sharing it with you. I'm also looking really forward to jumping back in and picking up where we left off. I'm curious to see how you are doing with chapter 10, independent samples on your own. I mentioned that I was going to provide a video, and here I am doing that. We're going to focus a little bit more on independent samples on Monday when I see you on the 12th. In fact, I want you to get familiarized with the case that I'm going to introduce to you in the chapter that's about moods, watching a movie and having the movie affect your mood. I'm going to run through the scenario, run through the calculations on the mat. I call the mat the paper. That's where we work stuff out. I invite you to really review this case, review the data, review the calculations, because on Monday, I'm going to put some context around it, because I think what's really important for you to understand as we begin to wrap up our time together is we've been working on a lot of, particularly in the second unit, in the second half in inferential statistics, we've been working a lot of calculations, but we've been working those calculations sort of in abstract, not really connected to how they're used. There's an important value and benefit to understanding just the calculations and the formulas. But ultimately, what I want you to leave this course with, and can you believe we're almost done? We're just a few weeks from the final. What I want you to leave this course with is the ability to read a peer-reviewed study and to grasp what's happening, particularly what's happening when the peer-reviewed study is quantitative, meaning statistics. But first, I'm going to sort of go through this in two sections. The first section, however, is I want to sort of focus on two concepts that we've studied in one sample and paired sample that's slightly different in independent sample. The concept is the same, but the execution is a little bit different. And specifically, what I want to talk about are these two things: the standard error, how the standard error changes from one sample, paired sample, and independent samples, t-tests, and also variance. In this chapter, in independent samples t-test, we get introduced to a new formula called the pooled variance. And when you first look at it, it looks a little gnarly. It looks very confusing, but I don't want you to be confused by it. You shouldn't be flummoxed by it by any stretch of the imagination. And I'm going to show you how we've been really doing the same thing, meaning progressing from one sample, paired sample, and independent sample. And that we're really doing the same calculation. It's just slightly different because of the context that's different in one sample, paired sample, and independent sample. So let's take a look at why the standard error and the pooled variance, defining it, why we use it, and how it changes. Okay, let's start with a sort of comparison across the t-tests. We have a one sample t-test, a paired sample t-test, and an independent sample t-test. And here we're going to look at what's different in terms of the null hypotheses for one sample, paired sample, and independent, how the alternative hypotheses are for one sample, paired sample, and independent sample, how they are different, the test statistic formula that we use for these three tests, and how the standard error is viewed. Okay, so let's start with a one sample t-test. The null hypothesis for a one sample t-test is that there is no difference between the test value and a known value. So the example that's used in the textbook is we know that the average weight of babies born in the United States, an industrialized country, is 7.47 pounds. So if we know that known value, we can test an observed or score against that known value. And so how it's written quite simply is null hypothesis, or HO, mu equals to 7.47 because that's what we're testing it against. So the alternative hypothesis is that there is a difference between the test value and a known value. And here we have to state our inequalities. It's either greater than or less than or not equal to. In other words, they're all unequal or inequalities. So we would write it HA, or alternate hypothesis, that there is a difference between the test value and the known value. And we would write it mu is greater than or less than 7.47 if that's what we're testing against. And if it's greater than or less than, we are only doing a one-tailed test. So when you go to the t-chart, you're only looking for whatever the A value is or the alpha value for a one-tailed test, either on the positive side or the negative side. Or we could say not equal to, which means it would be both sides. So that would be the only time that we would use a two-tailed test. So how it looks in terms of the test statistic is T equals M, which is what we're testing, minus mu, which is what we know. So it could be 5 minus 7.7, 6 minus 7.7, whatever it is that we are observing or testing against this known value. But I want you to pay attention to the denominator, which is the standard error. The purpose of the standard error is if we continue to take another sample, how would the samples vary from sample to sample? What would the mean be like from sample to sample? Or what would the test statistic be like from sample to sample? So the smaller the standard error is, the more precise we are in terms of our estimation of the population. So the standard error formula looks like this. Standard error equals standard deviation divided by the square root of n. Remember, the only other time that we put something, we divide something by n is for the average, right? We do that for the mean, but we also do an n for variance, or we do n minus 1. So just know that when we're dividing by n, we're putting it into the standard of the n size so that it relates to the n size. So when we're doing a square root of the n, we're getting even smaller. Remember, when the denominator is smaller, the product or the quotient gets bigger. So we get a bigger estimate, more robust estimate. So even though it's been a couple of weeks since you've seen this collection of hypotheses, test statistic, including the standard error, you understand that. We most recently looked at paired sample t-tests where we're taking a look at time 1 versus time 2. And so let's take a look at what the null hypothesis looks like. The null hypothesis is that there is no difference between time 1 and time 2. And so in other words, whatever it is we're looking at, whether it be before and after taking a test, or before and after taking a medication, what we're looking for is the difference. For a test, perhaps what we're looking for is an increase. We tested you one time, we taught you something, we tested you again, we expect the score to go up. And in that case, the formula is T2, or time 2, minus time 1. So when you subtract time 1 from time 2, we're going to get the increase. But if we're looking for a reduction of, say, symptoms, we test you or we measure you for symptoms, we give you a medication, and then we measure you again. In that case, we're looking for a reduction of symptoms. So the formula would be time 1 minus time 2. So when we subtract time 2 from time 1, we should see a reduction of symptoms. But in any event, what we're looking at is the difference. And you see that denoted here in the null hypothesis. The null hypothesis is mu difference is 0. If there is no difference between time 1 and time 2, no matter what it was, if it was 10 in time 1, and if there is no difference, it's going to be 10 in time 2. If it's 0 in time 1, it's going to be 0 in time 2. If it's 1,000 in time 1, it's going to be 1,000 in time 2. So no matter what we're looking at, we're saying that there is no difference. Hopefully that makes sense. So we're looking now at the alternative hypothesis, which is that there is a difference between time 1 and time 2. So the alternative hypothesis is mu d is either greater than or less than 0, because if there's no difference, and we're going to see if there is, it's going to either be greater than 0 or it's going to be less than 0. Again, if it's greater than or less than, we're only going to use a one-tailed test. But mu d could also not equal to 0, which means it's a two-tailed test. Again, you would go to the t-chart, look for the section for the alpha, either one-tail or two-tail. We would only use the two-tail for not equal to. For the less than, you're going to look for a one-tail, but on the negative side. For the greater than, it's going to also be a one-tail, but to the positive side. That makes sense? Let's take a look at the test statistic. Now we're looking at the mean difference between what we measured minus mu d. So quite frankly, ud is 0. We actually don't need it, but it's there so that you can see it. Now we have the mean difference minus the mu difference. But take a look at the standard error formula as the denominator. Now we're looking at not just the standard error, but the standard error difference, okay? And here's what the formula looks like. The standard error difference is the standard deviation difference. Here it was just the standard deviation. Here was just the standard deviation, that is the difference between time 1 and time 2, divided by the square root of n. Looks just like the standard error for a one-sample t-test. Now we're just doing a standard difference instead of standard deviation. Standard deviation difference, standard deviation. Now, when we take a look at the independent sample t-test, it's a little bit different, but the same idea, the same concept. In the independent sample t-test, what's different is group 1 and group 2 do not have to be the same n size. In a one sample, we're just using a one sample. So whatever the n is what the n size is here. For a paired sample, we're taking time 1 and time 2, subtracting one from the other, and ending up with a difference. And that difference is now the data set that we're using. So we're going to get the standard deviation of that difference between time 1 and time 2, and dividing that by the square root of n. So if we have 10 pairs, 10 is going to be the n. If we have 20 pairs, 20 is going to be the n for a paired sample t-test. However, the strength and the power of an independent samples t-test is that the n size for group 1 could be, I don't know, let's say 35. And the n size of group 2 could be, say, 29. So that they're not the same, which means their mean is different. Their values are going to be quite different. And so that's really what we're saying when we say it's an independent sample. The samples don't depend on each other. Here in a paired sample, they depend on each other. It's the same person at the beginning as at the end, or the same pair of people each time. So how we would write that is HO, or null hypothesis, the mu of group 1 is equal to the mu of group 2 if there is no difference. Doesn't matter what the n size is. The alternative hypothesis is that there is a difference between group 1 and group 2. So take a look as you see across, you can see the similarity and the slight differences. Here we're looking at the difference between time 1 and 2. Here we're looking at two separate independent groups. So the alternative hypothesis is the mu of group 1 is greater than or equal to the mu of group 2. Again, it would be a one-tailed test either to the positive or to the negative, or the mu of group 1 is not equal to the mu of group 2, which means two-tailed. So you would go to the t-chart and select accordingly. Now let's take a look at the test statistic formula. You can see the connection. Here the test is the mean of group 1 minus the mean of group 2, whatever that is, subtracted by the mu of group 1 and the mu of group 2, which we assume to be 0. Again, just like this UD, we actually don't need it. We don't need that, and we don't need that. But it's there to show that we are accounting for it, right? And look here at the standard error. It is a pooled standard error between the means of group 1 and the mean of group 2. So let's take a look at how we calculate that formula. This is where things start to look a little bit spicy, right? Still, the standard error is equal to the square root. Notice how the square root is covering not just the denominator, but also the numerator, okay? And notice how the numerator is the standard deviation, standard deviation difference. This is just a variance. It's a pooled variance because group 1 is, let's say, an n size of 35, and group 2 is n size of 29. So we're going to get a variance that is pooled together from those two different groups so that they have some sort of equal weighting. And I'm going to introduce the pooled variance to you in just a second. But if you can see here, all we did was stretch the square root symbol to include the numerator and the denominator. And you know that the formula for the standard deviation is just the square root of the variance. So that's exactly what we're getting. We're getting a variance from group 1 and a variance from group 2. And the square root of these two variances together is the standard error. Hopefully that makes sense. I'm going to show it to you on the map. You can see it in the example for moods when we get to that. But let's take a look at the next sort of element, which is really looking at how the variance changes. Okay, so let's take a look at how the variance changes from a one paired and independent samples t-test. You can see here that variance, the symbol for variance when it's a sample is S2 superscript. And it changes slightly from one sample paired and independent samples t-test. So the variance for a one sample is just simply the sum of squares divided by the degrees of freedom, because we're talking about a sample, right? And degrees of freedom is just n minus 1. So when you see the degrees of freedom, you just know that it's n minus 1, but we're just now talking about it in terms of degrees of freedom. How it looks in a paired sample t-test is a variance difference. You can see that the d here is subscript, is just the sum of squares difference divided by the degrees of freedom. It's now we're just, again, looking at the difference between time 1 and time 2, whatever that sum of squares is, dividing it by degrees of freedom, which is n minus 1. But take a look at how it looks in an independent sample t-test. This is a pooled variance. See, S2 means variance. Here is variance difference. Here is variance pooled. We take the sum of squares from group 1, add it to the sum of squares of group 2, and divide that by the degrees of freedom from group 1 and the degrees of freedom of group 2. So if the n size of group 1 is 35, degrees of freedom 1 would be 34. And if the n size of group 2 was 29, then the degrees of freedom for group 2 is 28. And then you would just divide that by whatever uh, the sum of squares 1 plus sum of squares 2. Hopefully that makes sense, that you could sort of grasp the concept. My idea was to give you a high-level overview, but then put it into context with the example, the sample that I want you to become really, really familiar with. So let's head back over to the textbook and take a look at that example, and I'll work it out on the map.